Okay, let's do example 5.6 on page 125 of your textbook. And this is an inclined plane problem involving a car on an icy driveway. So a car of mass m is on an icy driveway inclined at an angle 0 as shown in figure 5.11a. So I'll just write down what's given. You follow along in the book. But when I look at the picture, here's what we've got. We've got a horizontal. Here's the horizontal line, and then the car is on an incline. That is, the surface it's actually parked on is at an angle theta. So this is the surface the car is actually on. So this is horizontal. This is theta. And so let's draw our car. Here's our car. Okay, and you can draw it however you want. And it has a mass of m. So this is just really, we're keeping this very general. And basically, we're saying that this is an icy surface. We're just going to assume no friction. Oops, friction. No friction at all. All right. And so, and what are we trying to find? Well, in part A, it says find the acceleration of the car, assuming that the driveway is frictionless. So for part A, we want A, the acceleration of the car down the incline. And then for part B, it says, suppose the car is released from rest at the top of the incline, and the distance from the car's front bumper to the bottom of the incline is d. How long does it take the front bumper to reach the bottom? And what is the car's speed as it arrives there? So basically, we're going to say from here to here is a distance d. Okay, and we're going to start from rest, so v naught equals 0. And so we want to know how much time does it take to get here, and what's my final velocity when I get there. Okay, now really what part B is a kinematics problem. But to solve for the acceleration of the car, you need to use the procedure that involves Newton's second law. So let's go ahead and solve it. And so now I'm done with step 1 of the procedure. So let's move on to step 2. We're going to draw a free body diagram of this car. And so here's the car, like this. And I'm just going to draw the car. And so what are the outside forces acting on the car? Well, of course, gravity's pulling it down. Right? So, and it's pulling it straight down towards the center of the earth. And then there's contact force with the wheels and the incline. You can see it right up here. And let's take a look at the contact force between the wheels and the incline plane itself. It'll have two components usually. It'll have a component that's perpendicular to the surface and a component that's parallel to the surface. Well, the component that's parallel to the surface we call friction, but it says in this problem there is no friction. So the only force, and I'm just going to draw it as one force acting on the car, is a force like this. And that's our normal force. The normal force between this surface and that. And these are the only forces acting. There's just two of them. The earth, there's an interaction between the car and the earth. And since we're drawing a free body diagram of the car, we just show that the force of the earth on the car. And then the force of the ground on the car, and that's the normal force here. Now, let's do step 3. And what we do with step 3, remember, is we draw our x-y axis system. Now, in all the problems we've done so far, our x and y axis have looked like this, right? We draw x like this and y like this. And so, and you know what? We could do that with this problem, but we're not going to, because if you use this axis system, the problem is harder to solve. here's what you want to do. Now look, you know the car is going to accelerate down the incline. Here's a problem-solving hint. Always make either your x or y axis in the direction of the known acceleration. If you know the car is going to accelerate down the incline, let's make that the x direction. So what I'm going to do is this. I'm going to erase this axis system right here. And what I'm going to do is I'm going to say, look, down the incline is going to be my x direction, and perpendicular to my incline is going to be the y direction. And I'm going to do this because I'm allowed to. I can take my xy axis and tilt it to match my problem to make my problem easier. Now, to complete step 3, we have to break up our forces into their x and y components. But look, the normal force is now kind of defining what the y direction is. So it has no x component, it's all in the y direction now. But look at my weight. Now my weight is both in both the x and y direction. So I'm going to break it up into its components. Here's the y component of my weight, and here's the x component of my weight. Now here's a little geometry trick. Okay, let's suppose that the car was not on an incline at all, but maybe it was like down here. So I'm redrawing the car. Looks like a little Prius or something. Okay, now when here was my force of gravity straight down, and my normal force was straight up. But now look what I've done. I've rotated up by theta. I'm going like this, an angle of theta. I've rotated theta. So what have I done to my normal force? Well, let my finger represent the normal force. I've rotated that by theta. Okay, so here's when I look down here and I rotate by theta like that, that means that this angle between straight down and then to like that, this, what I'm arguing is that that's theta right here. If this is the angle of incline, here's theta right here. Okay, so now that I've got basically step 3 all done, well, actually, before let me finish step 3. Step 3 says to draw your x and y axis system, and then to break up the forces into their x and y components. And so here's my weight, but now here's the y component of the weight and the x component of the weight. And here is the angle of incline. So that means this is the adjacent leg. So this is the weight, and the weight is really m times g, isn't it? So I'm going to say that this is this component of the weight that's pushing it into the incline is the weight times the cosine of the angle of incline. And this component of the weight, that is the part of the weight that's trying to pull the car down the incline, is mg sine theta. That is, if this is mg right here, the mass times the gravitational strength of the Earth, that's my weight in newtons. Here's that force of weight. Here's the component of the weight that's being pressed into the incline. Here's the component of the weight that's pulling it down the incline. That's trying to make you go down. And so, so now I'm really done with step 3. So now I'm going to do step 4. Let's sum the forces in the x direction equals ma in the x direction. And I look at this and I say, hey, look, there really is an acceleration here in the x direction down the incline. But look at my free body diagram. There is only one force that's in the x direction, and that is the component of the weight that's parallel or in the direction of the incline. So this is going to be mg sine theta. And that's going to be equal, so right here, that's this force right here, this component of the weight. Look, the normal force is in the y direction. This mg cosine theta is in the y direction. Only this component of the weight is in the x direction. So that's equal to ma. And look, the mass of the car cancels out. Now what does that mean? The mass cancels out. That is awesome. That means that no matter how massive your car is, whether it's a little tiny smart car or a big, Lincoln compensator SUV, it's going to have the same acceleration. And we've answered part A now. A is equal to g, which is 9.8 meters per second squared, times the sine of the angle of incline. And that's my answer for part A. Okay, and this is, that's really a really cool result. And we'll talk more about it in class. I'm going to go over this again in class, but that's the answer. Now, let's, one other thing I want to do, even though it wasn't asked for, I'm going to sum the forces in the y direction equals ma in the y direction, just to be complete here. Now, let's look at the forces in the y direction. And I'll say, well, okay, well, in the positive y direction, remember I've defined this to be my positive y direction, is the normal force. And then this mg cosine theta, that's in the negative y direction. So plus a negative is really a minus mg cosine theta. Now, look, the car is not accelerating in the y direction, right? Your car is not going to leap into the air, as it goes down here. It's not going to sink into the ground, hopefully. So there is no acceleration perpendicular to the incline. So there is no acceleration in the y direction, which means this is 0. And what that means is that the magnitude of the normal force is equal to the weight, mg, this is the weight of your car, times the cosine of the angle of incline. And this is a very interesting result that we're going to use a lot in future inclined plane problems, especially when we get into friction. Now, let's move on to part B. Now that we have the acceleration, let's figure out the time. Okay, so for part B, this is all part of A, this is part A up here. But for part B, I want to find time. Now, what do without using final velocity. So which equation doesn't have final velocity in it? Well, that would be the third kinematic equation, which says, delta x is equal to v naught t plus 1/2 a t squared. Well, what's true about v naught? We said the car was going to start from rest, so this is 0. Now, what is delta x? Well, delta x, we're calling that d, so I'm going to change the variable name there, and that's d, is 1/2 a t squared. So now I can solve for t, and I already have an expression for a up here. So let's solve for t. T is equal to 2 times d over a. Take the square root. But let's substitute in what I know the acceleration is. So t will be equal to the square root of 2 times d over g sine theta. And that is my answer. This is my expression for time. Now, it's not in numbers, but look, just give me any distance d and give me any angle theta, and I'll be able to figure out how much time it takes for it to slide down the incline. That's assuming no friction. Okay, so that's the big assumption in this problem. It's a super slippery as you can get surface. Now let's solve for velocity without using time. The equation that doesn't have time in it is v squared equals v naught squared plus 2a delta x. Well, again, this is 0. So v is equal to the square root of 2 times a, but a is g sine theta, and delta x is d. Now that looks a little awkward, so just to make it look a little prettier, I'm going to rewrite this. V is equal to the square root of 2 dg sine theta. And that's my answer for the velocity. There you go. That is example problem number 6 on page 125.